So before getting back to material, I'll remind you that the first of the problem sets is due Wednesday at 1. This time, don't shoot at 1 o'clock. It's a deadline, not a target. Try early. Please make sure you can log into the problem set website and at least see the problems soon to make sure that nothing goes wrong at the last minute. Hopefully, I've seen many of you have gone in already, one way or the other. And between now and Wednesday, I have both of my office hour periods, this afternoon at Alderman Cafe and Wednesday morning in my office downstairs. Any questions, issues about problem set? The first exam is also coming up, I believe, the 16th. Is that the right number? Just to warn you, it sneaks up on me too. I don't even have my own list here. Be aware it's coming eventually. All right, so where I left off last time in talking about ramps is I'm taking a wagon up and down a ramp, and I claim that something interesting is involved in going up the ramp that's not so, it's different from going down the ramp. It's a lot harder it's more work going up the ramp than down the ramp. And the issue that comes up is literally work. You're doing physics work on the wagon, dragging it up the ramp. It is doing work on you going down the ramp. So just to remind you of this, I talked about it, but I never sort of showed you that when you're going up the ramp with a wagon, and I'll go to sort of the middle part of the story where it's going at steady pace. For it to go at steady pace, I have to pull uphill. I have to balance the downhill ramp force. So I'm pulling uphill and it's moving uphill. That's what's required to do work on something. Am I exerting a force on it? Yes. Is it moving in the direction, a distance, in the direction of my force? Yes, I'm doing work on it. On the other hand, if I let it go downhill like this, now it's pulling, see, I'm still pulling uphill, but it's moving downhill. I'm doing negative work on it. I am actually sucking energy out of it. From its perspective, it's pulling me downhill. As I move downhill, it's doing work on me. So the transaction's complete. On the uphill trip, it gives me, I give it energy and it takes energy out of me. On the downhill trip, it takes energy out of me and I give it energy. All right? So, I said, no, that's all wrong. Let me say it again. Pay attention to what I say. Uphill, I'm doing work on it, and it's doing negative work on me. So I'm giving it energy and losing the energy myself. On the way down, it is doing work on me, and I'm doing negative work on it, which means it is giving me energy, and I'm taking energy away from it. Got it right that time. All right, too much complexity in the language. When I left off in this view graph, the reason I brought this guy back is work is actually, has quantitative meaning. There's an amount. The work that you do is a specific amount, and how do you calculate that? Well, it's a force times a distance, so it's going to have units of force times units of a distance. And that means that if suppose this weighed 1 Newton, it doesn't, but we'll just pretend it does. And suppose I lift it 1 meter up. That means in order to support its weight so that it can move at constant velocity, I have to exert a 1 Newton force on it. And if I exert a 1 Newton force on it as it moves 1 meter, I've done exactly 1 Newton meter of work on it. It's no big surprise. The Newton meter is so important. That is the unit of work. It's the unit of energy. It's so important that it has its own name. It's called a joule, spelled Joule, as opposed to like celebrities. Okay, all right, or what you wear in your finger, Joule, after a physicist. So that's 1 joule of work that I did. And if I let this down, it does 1 joule of work back on me. Is that okay? Newton meter is equivalent, so they're equally good. It's just one's wordier than the other. One's a single syllable. All right. So back to this one, which I think I sort of finished on, is that energy can take, so work is the mechanical means of transferring energy from one thing to another. And I'll remind you again that it is a very narrowly focused story. If you want to see whether I'm doing work on the basketball, pay no attention to anything else except where I touch the basketball. If I'm not touching it, no, I'm not going to do work on it. So I have to touch it. I have to push on it, and it has to move a distance in the direction of my force. So you look only here. And if I'm pushing on it, yes. And it's moving a distance in the direction of my push, yes. I'm doing work on it. How much? It's the force times the distance. All right? So all the details. And it's easy to get distracted by the details and to wonder where the energy that I am giving the basketball came from. Did it come from me, or was it given to me in the process? It doesn't matter. It's just my hand at the ball. In lifting the ball, the type of energy that I gave the ball, if I lift it, is a potential energy, as opposed to if I throw it, it becomes kinetic energy. That energy you can see. Potential energies are more subtle. You have to look for them. They're hidden in the forces between things or within things. In this case, it's going into the force of gravity. I'm stretching the ball-earth connection. I'm pulling them apart as though I were stretching an invisible spring. And so the energy stored in the earth and the ball and the force between them, because the earth is so huge, so massive, it's so hard to get the earth to do anything significant, that when I do this, I do it entirely by moving the ball away from the earth. And when I let it back down, it's entirely the ball going towards the earth. Okay, it's not entirely. If you look at 30 digits in 0, 0, 0, 0, 0, 0, 0, 0, 0, there's a little 1 down there. There's a tiny movement of the earth. I can shake the earth. I'm shaking the whole earth right now. Okay, but you would never notice. Okay, so what's the point of this tangent? Or not, it's not a tangent. When I do this, the energy is really invested in the force between the earth and the ball. By tradition and convention, we give it all to the ball because the earth is never going to get hold of this energy. It's really the ball is going to get it back when I let go. The earth gets barely a tiny fraction of it. So this energy, potential energy, we really just associate with the ball as though it were in there, okay? It's called gravitational potential energy because, of course, it's stored in the force of gravity. In some classes, you may have just simply called it potential energy without even describing what force is involved. But there are so many forces involved, where there are enough of them in this semester that I want to be specific. This is gravity, as opposed to what? As opposed to magnetic or electric, or we'll see other things. Okay, so by lifting the ball from this height to that height, I have given it energy. I did work on it after all. The energy is now in it in the form of gravitational potential energy. And if you think about how much work you have to do to lift a ball that weighs a certain amount, so we know its weight, and I have to push up on it with a force equal to its weight, and then it moves a distance. The amount of work that I have to do in lifting it is its weight, because I'm going to have to push with a force that strong, times how far I lift it. Force times altitude. Weight times altitude. So that's this relationship at the bottom. It's just worth knowing, and it will come up in the first problem set. Is that true? Probably, I'm not sure. As you lift the ball upward and put it to a higher altitude, its gravitational potential energy is increasing, and the amount it's increasing by is its change in altitude times its weight. That relationship, it says altitude. Altitude above what? That's something that you can choose. You can choose what you call altitude 0. We could call it the table. That's altitude 0, at which point it's got no gravitational potential energy. If you lift it up, now it's got 1 joule, according to my pretend weight. 1 joule of gravitational potential energy. But then you might go, well, what about when it's on the floor? Well, our choice of 0 wasn't a great choice. That's even lower. So that, using this as the 0, that's actually negative, about negative 1¼ joules. It doesn't matter. It's the relative changes that always matter. What's the real 0? Who knows? You have to drill a hole in the earth and let the ball go even lower and lower and lower, and it gets complicated after a while. So gravitational potential energy is just weight times height. all right? Well, that brings us to the ramp story. And the ramp story now, with all this, hopefully this background that you can sort of assimilate, the ramp story is essentially this, that in lifting this kid, that kid weighs almost 50 newtons. So to lift it 1 meter up to, say, that height, that's going to take 50 newton meters of work. I'm pushing with 50 newtons up here, 1 meter. I've done 50 newton meters of work, which is 50 joules. Doing it that way was hard, because I have to push hard. I don't have to push for very far, so it's a big force, little distance. Right? I'm going that meter as quickly as I can, straight up. I'm increasing that altitude. Instead, the energy ends up as 50 joules of gravitational potential energy. And if I let go of this, of course, it'll become kinetic, and I'll regret it. What the ramp lets you do is lift the heavy kid from height 0, the original altitude 0, to the destination altitude. I need a longer ramp. I imagine the ramp's real long, and I get to this height. I will have done it. I will have done the work actually of lifting it to that height. It will be the same amount of work, because the let me show you that it's the same amount of work. I should say where I'm going so that you know where I'm going. That regardless of how you go up a ramp, from height 0 to height 1 meter, altitude, you would call it what you like, regardless of how you go up the ramp, whether the ramp is steep or shallow, or just a ladder, you're going to do the same work. It doesn't matter the path you take. And how would you know that? Well, it's because here's the before. Remember I told you you can either watch the transaction to figure out how much work you're doing, or you can look at the before and after and see how much the energy changed, and you know the work you did had to be that difference. So here's the before. The kid is at altitude 0. Don't look. Oh, kid's at altitude 1. It's got 50 joules of gravitational potential energy. I must have done 50 joules of work on it to get it there. That's the before and after view of the world. And I told you not to look because you didn't see how I got there. I might have gone right up a ladder, or I might have used a ramp. It doesn't matter. I will have done the same amount of work. You're okay with that, or questions about that idea? Why it's got to be the same amount of work however you do it? You could throw it up there. It might have been me. I'm killing my own question about, do you have questions? I could just throw it up. Wow, that would be just as good. If it got up here and it's sitting up there, I did 50 joules of work on it, somehow or other. Shot put. So, no matter how you get up there, it's the same amount of work. That means that the work done while going up a ladder, which we know, 50 newtons of force, 1 meter of height difference, that's 50 newton meters, or 50 joules. I must be doing the same work going up the ramp. And I am. If you recall, without my hand here, this would experience a downhill force, what I call the ramp force, which is not very strong. I can measure it, actually, by replacing my hand with a scale that will tell us how strong, how hard it is pulling. I am balancing the ramp force right now with a force of about 11 newtons. So as I go up the hill, remember I got to get started, so I'm going to have to pull briefly extra hard. Okay, I did. And now we're going at constant velocity. I still injured this poor wagon. I need to fix it. Those crashes the other day took a toll. Anyhow, to go at constant velocity on this ramp, I don't have to pull with 50 newtons of force. That's for going straight up. For going on this ramp, I only have to do a quarter of that. Not even a quarter of that. Up the ramp. But I have to go much farther. So what the ramp lets you do is it lets you do the work you need to do in lifting something, a certain altitude up, but you get to change the relationship between force and distance. With the ramp, you get to use a smaller force. because you're not lifting the whole weight of the object. You're pulling it up a ramp. You're just balancing the ramp force. But you have to go farther because you're going along the ramp, and it doesn't take you uphill. It doesn't increase your altitude all that quickly. So what we could do for ages is play with the different ramps. If we make the ramp a more shallow ramp than this, instead of being like that tilt, we go to this tilt, or less. The ramp force will become weaker. If you recall back to the origin of the ramp force, it's the support force up at an angle and the weight down straight. And they're getting closer to being able to cancel when I make that ramp almost horizontal. So the ramp force is dinky, means pulling it uphill is easy. Wow, we can get the blocky kid up 1 meter, no problem, except the ramp now has to be really long to rise a meter. So you don't get something for nothing. This uses a very small force for a very long distance. It's that first entry up here. Little force, big distance. Alternatively, we can go to build the ramp up like this, and now we lift the blocky kid up 1 meter pretty quickly. We don't have to go along that ramp very far before the kid is up 1 meter above the ground. But the force we're going to have to exert is much larger. So we haven't gotten something for nothing now. It's now a bigger force, smaller distance. And finally, if we go all the way to vertical, we get the full weight. The force is now the full weight of the kid, but the distance is down to 1 meter. That's the minimum we possibly can get. Okay? That is the beauty of a ramp. And as one last sort of hurrah about this is most of the simple machines that you encountered back in whatever school it was, there are exceptions, but most of them are about doing work, the work you want to do, splitting a block of wood by a log, by shoving a wedge into it. You're trying to do the work you need to do to split the wood, but you want to change the relationship between force and distance. You want to use a bigger force for littler distance, or a littler force for a bigger distance, one of those things. That's the underlying story behind all these simple machines, or many of the simple machines. They let you play with the force and distance. The problem set is about the fitness center and stuff. If you go over to look at the fitness machines, forget the problem set, look at the fitness machines, they're all full of things that are exchanging force for distance and distance for force. A lot of what you're doing is work. Force, you push something up and you do work on it, you lower it down. If it's just a free weight, it's doing work on you, which means you're doing negative work on it. Some of the machines don't behave like that. They do weird things like you have to push them up and you have to pull them down. You're doing work both times. All right? Last thought about ramps. Practical example, the access ramps that are all over grounds and required by the ADA. They have a maximum steepness, and I forget exactly what it is. There are 2 maximum steepnesses, and there's a special criterion for having the steeper version. But in any case, it's like 12 to 1, I believe. I mean, it's one I've known and then forgotten 1,000 times. You can't make them too steep. If you make them too steep, people cannot get up them. The forces involved trying to propel yourself up in a wheelchair, for example, are just too severe. You can't deal with it. So they have to be a certain steepness and no more, unless there are constraints on the place you're working in. And that means that often they have to go. You just can't make it that long in one straight pass. You have to go and then turn and then go up again. So as you walk around grounds, look at the access ramps. You'll see how they're working to try to get the right steepness, no more, no less, more or less, and working within the constraints of a historical campus. All right? Any questions about ramps and work and energy, at least to this point? Okay. So seesaws. Seesaws are a disappearing toy. They do exist in Charlotte, but there was a period when I couldn't find them anywhere. Similarly, I couldn't find any merry-go-rounds, the spinning toys. They still exist too. Greenleaf Park. Anyway, seesaws were, any playground would have a seesaw when I was a kid, but they sort of disappeared in part because they're a little dangerous. I don't know whether you guys sort of even have ever dealt with seesaws, but just to remind you because I can, right? Two kids playing on the seesaw. They both get on, one kid on one side, one kid on the other side. They rock back and forth. And then this kid sees some bright and shiny thing over here and goes, right? So that kid ends up surprised, bites his or her tongue. The other possibility is the really big kid comes along, right? And we have an early astronaut. Okay. So, that was new. I haven't thought of that one before. Okay, astronaut, yes. Bowling ball, no. Okay, anyway, seesaws are, apart from being sort of rare, they're the story of rotation, believe it or not. The motion that matters in a seesaw is a rotary motion about a pivot. And that's my reason for using it in this, for bringing it up here, is just to give us some idea of how rotary motion works. It shows up in so many things, in a car engine, a generator, wheels, and wind turbine. So might as well have some sense of how rotation works. All right, so a seemingly unrelated question, but it is related, is this one, and these are my props for it. You and a child half your height lean out over the edge of a pool at the same angle. So there's the pool. You lean out over the pool at the angle, and the kid next to you is leaning out over the pool next to you, the pool also. And you both let go at the same time and tip over into the pool. Your feet remain on where they were. Who hits the water first? You understand the question? Still with the question? So I won't do it here because I'll break everything. So there's you. You're nice and tall. There's the kid. And you both lean out over the pool, and then you let go at the same time. Who hits the water first? How many think A, you hit first? How many think B, the kid hits first? Okay, the majority are going for the kid. I will, I'm supposed to, according to my plans always, I'm supposed to come back to this, but you now all can place your bets. There's the kid, there's you, ready, get set. It's not even close. The kid hits first. The short person hits first. And what we'll see is this, to give you a preview of this, it's an acceleration issue, but not an acceleration like we're used to, going left and right and speeding up or slowing down. It's an angular acceleration. It's a rotary version. And so here's the kid angularly motionless, and there's the kid rotating, and that's an acceleration. The change from not rotating to rotating is an acceleration. So we're causing angular acceleration of you and the kid. It's actually gravity's doing it. And the question is, who accelerates fastest and builds up rotational velocity for fastest? And it turns out it's the kid. And the reason is because if you remember Newton's second law, in the world of what's called translational motion, where you're going somewhere, acceleration is caused by a force and impeded by a mass. Force over mass gives you acceleration. In the world of rotation, it's not a force anymore, it's a torque. It's a twist. And so that's the cause of angular acceleration. I'm getting ahead of the story here, but you'll see it come down. This is the pass number 0 through the material. So a torque is going to cause angular acceleration. And there's going to be a resistance to it, an inertial resistance. It's called rotational mass. I call it rotational mass. It has a fancy name among physicists known as moment of inertia, which I find relatively opaque. So rotational mass is good enough. So there's an influence that causes the angular acceleration, that is torque. And there is a resistance to angular acceleration, an inertial resistance, that's rotational mass. And the kid has a certain amount of torque based on its weight and shape, and it has a certain amount of rotational mass based on its mass and shape. And it's pretty easy to get this guy to go back and forth. There is not much rotational mass here fighting me. This would be mass fighting me. This is rotational mass fighting me. You okay with that idea? This is easy. This is terrible. It turns out that because this thing is so long, and it's twice the mass as the other one because there's twice as much wood here, this thing's way hard to shake like this. If you don't believe me, try it after class. You can sneak up here and you go, oh yeah, this one's easy. Ah, okay? That's the dominant effect here, is that rotational mass is so big for this long thing with a lot of mass. It's got so much motion far from the pivot that slows everything down. And so you, the tall thing, have too much rotational mass. You're late to the water. So okay as a preview? Okay, so we'll do it right in a second. So some observations about seesaws. That's my context in which to look at all this stuff. A balanced seesaw rocks back and forth easily, and that actually sort of recognizes the whole notion of what it is to be balanced. A seesaw that is not balanced, if you've ever, again, done seesaws, it doesn't rock back and forth much at all. Mostly, like the heavy kid just sits there on the ground, and the light kid's like, look, I'm up here. Okay, so you got to get it balanced. What's balanced? Okay. In terms of playing on it, equal weight children can balance it nicely if they sit equal distances from the pivot. If they are unequal in weight, sitting equal distances from the pivot's a bad idea. You don't get much, not much happens. This is, forget these guys. There, this is essentially a balanced seesaw. This is how you want to play it. If this kid decides to sit there, it's just boring. Nothing much happens. On the other hand, if you have a really heavy kid, blocky here, okay, the whole neighborhood gets out here. We're stuck. What do we do? Well, it's usually a parent. Okay, right? The parent scoots in here to play with little Throckmorton. Here we go. Oh, I've got to scoot in further. Okay. So there the parent is successfully, they're balanced again, but you got to bring the heavy person in close to the pivot. So all this there's physics behind all of these choices. The last thing is if the two kids, this you can rock back and forth, but getting it to reverse takes a little bit of doing. This has, incidentally, a fairly large rotational mass. You got a lot of mass far from the pivot, as we'll see. But if you bring the kids in close, like this, or you're just one kid standing over the pivot, which is, I never did that as a kid. Stand over you can teeter the thing back and forth violently with great ease, because there's very little rotational mass left. Everything's in close to the pivot. Okay, so these are just observations about seesaw land. A bunch of questions to look after, and I will try to go through them efficiently. This is one of these sections that I can get bogged down in, so I will try not to bog. All right, first question is, how does a balanced seesaw move? And the answer is that it moves at a constant rotational speed about a fixed axis in space. If that sounds vaguely familiar, it's because it's another inertia story. We saw with the skater, you know, how does a balance, how does a skater that's experiencing no external influences, which is something like balanced, how does that skater move? The skater moves at constant speed in a fixed direction, namely at constant velocity. That's life as a skater when you're not turning or speeding up or slowing down. There's the same story for rotation. And just to make sure it's clear that what I'm doing, I have told you now it's fair length about motion where you're going somewhere, which is known as translational motion. So when you translate, and it has nothing to do with languages, I've got a position, I've got velocity, I've got acceleration, I've got mass fighting that, and I've got forces causing it. That whole story comes over into a second type of motion, just rotational motion. So instead of going somewhere, you rotate, you change your orientation. That's rotational motion. Objects frequently do both at once. Some objects do only one. A seesaw is an example of one that does not translate. It has a pivot stuck through it, so it can't go anywhere. And therefore, it's a purely rotational story. And there have been years when I tried to do wind turbines, which is also a purely rotational story, but it was just harder to work with. I came back to seesaws. All right, so I'm going to reintroduce 5 physical quantities that are quite analogous to the 5 physical quantities of translational motion. These are the rotational versions. And I sometimes will switch between calling them rotational and angular. There are official, usually it's angular is the official word, but who cares? It's the same story, okay? So just as there is position, there is angular position. And it tells you how something is oriented. So for example, it requires a reference too, not surprisingly. So if we call north, that's north. If we call north angular position 0, then any orientation away from that can be described with 2 pieces of information. An amount, which is an angle in a sense. An amount, for example, 90 degrees. My angular position right now is now 90 degrees. This was 0. This is 90 degrees. But we need one more piece of information because you don't know whether it's 90 degrees like this or 90 degrees like this or 90 degrees like this, right? All those things are 90 degrees. What we need is we need an axis, like a rotisserie axis, about which I need to rotate in order to reach the destination orientation. So for example, I rotated 90 degrees about a vertical axis, like a spit going through me from top to bottom. Okay? So this is 90 degrees. This is 180 degrees. Oddly enough, if I continue 360 degrees, I've turned things around 360 degrees, like Yogi Berra. All right? So, but still, you're seeing my orientation change, and that's my angular position taking different values. So, Fiona? Fiona's question is, how do I know which 90 degrees I went? The vertical axis pins things down a lot. For example, 90 degrees about the vertical axis does not include this possibility, right? But it does include this possibility. Uh-oh, that's a 90 degrees around a vertical axis also. You see, that's one ambiguity. That's all there is. The 2 choices for 90 degrees are about a vertical axis are this or this. They're both 90 degrees about a vertical axis. How do you solve this? There is a convention that has been adopted a bazillion years ago, back when the dinosaurs ruled the earth. It's called the right-hand rule, and it works like this. That vertical axis has 2 directions in it, up and down. They're both vertical axes. We assign, by convention, the vertical axis up to this rotation. I just rotated 90 degrees up. I know up seems like it has nothing to do with my motion, what I just did, but it does. It describes the axis about which I rotated and which way I rotated on that axis. I rotated upward. How does the right-hand rule help you with this? You put your thumb along the axis, up, your fingers of your right hand, no left hands in this. I mean, you may be left-handed, sorry. It's right-hand hegemony here. You have to use your right hand. And your fingers point in the direction of the rotation. Does it matter that you remember this? No. You just should know that it's there. It's like, there's so many stories I can tell you, that you have to learn what's your right hand. If no one tells you what's your right hand, your entire growing up, or anything like your right hand, you can't figure it out just by having someone talk to you over the phone. You need an artifact, in effect, to know what right hand is versus left hand. And you learn this by memorization, pure and simple. They're not otherwise distinguishable. The physics of the world has a symmetry to it. It's very hard you can't distinguish right hand from left hand without being told. I'll stop. Anyway, so this is rotation up. In contrast, this is 90 degrees down. Is that okay? So the point of this then is to say that angular position, which is what this is called, consists of an amount, which is the angle through which you rotate away from zero, and the axis about which you rotate using both directions of the axis and the right-hand rule to figure out exactly which rotation we have in mind. So this is 90 degrees down. This is 90 degrees up. This, remarkably, is both 90 degrees down and up for position because things repeat. So it happens with angular position. All right? Angular position, not a terribly useful physical quantity, even for physicists. What is more useful for physicists is changes in angular position, because they involve movement and going from one position to the next. So angular velocity turns out to be a useful, it's a useful quantity in physics. I'm thinking that you all encounter, for example, RPM, revolutions per minute. This shows up in your car engine. It shows up on other things turning. Back in the days when people listened to phonograph records, it mattered too. You know how fast. If you use the wrong RPM on your phonograph record, everybody sounds like Alvin and the Chipmunks. That's how they make Alvin and the Chipmunks. You just turn up the speed too fast. So RPM is basically the speed part of angular velocity. Angular velocity is the measure of how your position is changing with time. And I'll show you about 90 degrees per second, because if I go any faster, I'll get up, I'll tip over, right? So this is about, it's about 90 degrees per second, angular velocity. And angular velocity has a direction as well. This is 90 degrees per second. I can't do this. 90 degrees per second. You can imagine me doing cartwheels, right? Very slowly. I cannot imagine myself doing cartwheels. I would usually fall over and cripple myself on the floor. But any way I rotate 90 degrees per second, it all counts. So again, you figure the direction part is the axis about which the rotation is occurring. The only one that I can do conveniently is a vertical axis. And this is 90 degrees per second, but this is also 90 degrees per second. How do we distinguish them? Right-hand rule again. This is 90 degrees up, 90 degrees per second up. This is 90 degrees per second down. Okay? I can start playing with this toy here. This guy, I can also get going. That's about 90 degrees per second. And in this case, you show me which way it's rotating. with your hands? Which way is it rotating? It's a horizontal axis, right? That's the pivot. And it's going away from you guys. Ooh, that's away. This is toward you. Is that okay? Yeah. Yeah. I'm trying to think which movie it is. Yeah. I can do this. You guys can't, right? Yeah. All right, so that's angular velocity. Anything else I wanted to say with this? No, good enough. Okay. Third physical quantity of rotational motion to talk about is the influence that causes angular acceleration. And it's called torque, spelled T-O-R-Q-U-E. Torque is a twist. It's what, when you twist something, you're exerting a torque on it. Torque shows up from time to time in things like people work on their cars or have cars, buy fancy cars with a lot of torque, or it's a very useful quantity if you're doing any sort of rotary work, as in tightening and loosening nuts and bolts. You exert too much torque on a bolt, you will break it. Twist it too hard. Okay, so it's a glorified name for twists. And with those three quantities now, we can look and see what happens to an object that is experiencing no torques. And incidentally, torques, several people can twist the same object, in which case their influence on the object is summed. You add it together. You look at the overall torque on the object, not surprisingly called the net torque. So objects respond to the net torque on them. And here's an important story, and that is, it's Newton's first law, not for translational motion, which is what I did on day one. This is Newton's first law for rotational motion. It has a couple of extra words thrown in that we'll come back to, but basically it says, and I'm now going to oversimplify it, it says that an object that's not being twisted turns at constant angular velocity. It has to have some extra words in it. The object can't be wobbling, and it's got to be rigid. It's not allowed to change shape. If it changes shape, it can do things that mess up the first law. And if it's wobbling, the first law is too simple for it. It's overly simplistic. But basically, it says you leave something alone, assuming it's rigid, it will turn at constant angular velocity. And that's what this beam here is for. This is my super simplified seesaw with no ground. I got rid of the ground. So seesaws encounter the ground all the time, so they can't do a full rotation. But this guy can. And if I get it started, so the story didn't start until I got it started. Now it's experiencing no overall torque. And that's what it actually means to be balanced. It's balanced, meaning that the gravity in particular exerts no torque on it, no twist due to gravity. As a result, it turns with constant angular velocity. Once you get it started, it's not quite, it's pretty close, but it's not quite. Once you get it started, it just keeps going. Steady pace around the same axis in space. So this is turning away from us, and it's turning steadily away from us. Same tick, 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 same angle every second. And that is an example of rotational inertia. You leave something alone, it keeps doing what it was doing. If it was motionless, it stays motionless. Pretty close. In fact, so it stays motionless. It can be at this angle, in principle, and stay motionless. So a balanced seesaw, which is one of my questions in here that I'm just going to give away the answer. A balanced seesaw, meaning a seesaw that's experiencing certainly no torque due to gravity, and presumably nothing else. It can be motionless at any angular position it likes, but it can also be turning at constant angular velocity. Steady turning. Why does it turn? Because of inertia. It doesn't need a torque to keep it turning. It just turns steadily because that's the nature of things in our universe. You get them spinning, they stay spinning. some of the extreme examples of that are some of the satellites. Satellites are often set spinning to improve some of the stability of their behavior. There's some classic examples where satellites were set spinning one year and then visited again by astronauts years later, and they're still spinning about the same axis in space. You get them started, they just keep on going. Newton's first law of rotational motion in action. Is that okay? Let me pick off a few more tidbits here before calling it a day. Why does a seesaw need a pivot? And that is essentially to stop, to prevent translational motion. You want the seesaw to stay put translationally. You do not want it. You put the kids on there and then you go off and have a cup of coffee on the park bench. You do not expect to come back and discover that the seesaw has headed off to the shopping center. So you pin it down with a pivot. And also, there's a problem that something needs to support the weight, the overall weight of the system against the pull of gravity that would cause things to fall. So you also want that pivot to support the weight. So the pivot does two things. It keeps any horizontal motion at bay, and it also prevents falling. And ultimately then distinguishes the world of translation and rotation and allows only rotation. Not a very complicated story there. Why does a lone seesaw rider plummet to the ground? So that's this example where, let's take them both off at once. You put just one kid on the seesaw, and boom, terrible trouble. And the reason for that is that the seesaw rider, the one seesaw rider there on the right, exerts one and only one force on the seesaw bar. It pushes the seesaw bar down. I mean, basically, the seesaw bar and the kid, they both push on each other. The seesaw bar is trying to support the kid's weight. The kid is in the process of falling and therefore is pushing on the seesaw bar to get it out of the kid's way. The two of them together conspire to push down on the whole system with the help of gravity. And that causes rotation to start. The seesaw bar begins to rotate faster. Let me just illustrate it with my hand. I'll play kid. The kid here gets on the seesaw and pushes down and causes rotation to start. Well, that's a force. The kid exerted a force on the seesaw bar. And forces are the influence for translational motion. Why are they showing up in a rotational story? The answer is that the world of rotation and the world of translation aren't completely separate. You can interpret or describe translational motion using rotational language, or rotational motion using translational language. Like, here I am rotating, and I could go look at my finger. This finger is going first towards you, velocity towards you, velocity towards the right, velocity away from you. You can break it all down in translational world, but it's just messy. It's easier to say this is a rotational story. Similarly, this can be described in terms of rotation. It's just really messy. So they aren't totally separate worlds, and it is possible to use a force to produce a torque, or a torque to produce a force. Anybody who plays lacrosse, when you whip the ball like that, you're using a torque to push the ball forward and make it go real fast. So torque and force, they're like this. They're best buddies. In this case, I'm using a force to produce a torque to cause rotation to begin. And it involves levers and lever arms. And I'll talk about levers and lever arms on Wednesday.